right. Yeah, click. Yeah, can you choose full screen or presentation mode? Yeah.
Oui, je suis en mode présentation.
You stop sharing screen, Brice. Hello, Brice, you stop sharing the screen.
Right, there is some echo from coming from you.
It's okay, là. It's okay.
Let me see.
No, so now you're sharing your browser. Yeah. Okay.
You should share your main screen. Okay, good. Yeah.
Can you put it in the full screen?
Yeah, full screen.
Full screen.
Yeah. Oh. I think it's F5 on the right. You click. Yeah. Presentation mode. And okay, it's fine. Or maybe you should choose presentation mode. But you're having a lot of echo, so maybe you should turn off one of your devices. Okay, I think it's good now. Huh?
It's good, thank you.
Okay. But I don't know, the top seems to be cut off. Can you choose presentation mode, not full screen?
Presentation mode, okay.
Maybe at that top, is there presentation mode?
I think you have the live stream in
the
background.
Better. Yep, perfect.
Because we're...
It's okay now?
Yes.
Good.
So you start when the chair tells you to start.
Oh, I'm supposed to start?
No. Brice will start when the chair tells him
Brice,
to start.
sorry. Okay.
Can I start the presentation?
Please hold on. Richard, can you start?
Sorry. Actually, I'm confused. Am I the chair this morning? Or are you the chair?
Oh, I'm not supposed to be the chair.
If you were supposed to be chair, I would appreciate it.
Okay. So, yes, you may start, Brice. So, welcome everybody. So, welcome to the fourth day of the first workshop of the USAfrI Initiative in Electronic Structure. So, Professor Brice Malonda Bungu from Congo shall be sharing with us the first keynote talk on structural electromagnetic and anisotropic properties for these compounds from DFT calculations. So we welcome Professor Brice. Yeah, so you may start.
Okay. Hello, everybody. I am Brice Malonda Bungu from MnBi University, Brazzaville, Congo. We are going to talk about structural, electronic, magnetic, and anisotropy properties for manganese, bismuth, oxygen on manganese, bismuth, tantan on manganese, bismuth, and oxygen on bilayer tantane on manganese binmus system, DFT calculation. In this talk, we are going to about motivation, goals, first theorem approach, computational method, result and discussion, and we will end with the conclusion. About the motivation, MnBi and film possess unusual physical properties and are particularly suitable for memory application using laser pointing and magnetic readout. MnBi also is a promised ferromagnetic material for application at elevated temperature due to its high current compared to sizable magnetocrystalline anisotropy, increasing temperature.
Yeah, Brice, please, can you adjust your mic because everything is breaking. It is cracking.
Yeah. Sorry.
Yeah, we can hear you now. So what happened before? It was cracking before.
Okay.
Okay, it's good now.
The control of anisotropy direction enable application of manganese bismuth films in permanent magnet, spintronic device, or magnetic mechanical systems.
Okay, go ahead. Yeah, fine.
However, fabrication of manganese bismuth and films with ferromagnetic low temperature phase is conventionally difficult. This is due to the peritectic manganese and manganese oxidation. Structural characterization done by Lee et al. Reveal a formation of manganese bismuth in the has deposited high beam bombarded sample. And vacancy annealing further promoted one of MnBi brain with C-axis orientation, leading to the perpendicular magnetic anisotropy. This advancement is attributed to the enhancement, interdiffusion, and reaction of manganese and bismuth in the ion beam bombarded these films. A stability test of 150 days in air revealed a remarkable reduction in ferromagnetism due to the manganese bismuth decomposition. Zhang et al. Have studied the manganese 10-film change from isotropic to anisotropic after magnetic field annealing. This MnBi film may have out of plane or in plane anisotropy, depending on the direction of the applied field during magnetic field annealing. Also, Chen et al. Have prepared a mica substrate MnBi film that have the easy direction of magnetization perpendicular to the film plane. calculations shown that the rating magnetic field can be reduced to less than 10 OE by using a memory plan consisting of discrete square of manganese bismuth. In the same way, Wu et al. Have grown manganese bismuth thin film by using plasma-assisted molecular beam epitaxial technique. This film exhibits a spin reorientation at about 90 Kelvin due to the magnetization change from C-axis to EB plane, which is related to the abnormal temperature dependence of the lattice parameters. Sun et al. Have fabricated the low temperature phase manganese bismuth thin film with a perpendicular. The oxidation effect of manganese bismuth films was observed and systematically analyzed. The influence of oxidation on magnetic properties was investigated for sample experiencing the 19-day exposure to air. The saturation magnetization of manganese bismuth thin film was reduced by 35%, while its coercivity was last by 23% due to the oxidation. Almost no change in structural and magnetic properties were observed in the MnBi thin film, protected with a tantalum capping layer, even after prolonged exposure to air. Moon et al. Studied layer number dependence of magnetic property of MnBi films. These 10 films were fabricated using multi-layer deposit and in-situ annealing. They conclude that the highest magnetic property was found for 9 and 10 layers. Theoretically, Antropov and al. Studied the magnetic property effect and electric correlation in MnBi ferromagnet. The electronic structure and numerous magnetic properties of manganese bismuth magnetic systems are investigated using local spin density approximation with U-bar effect. The inclusion of the anisotropy pairwise exchange interaction between bismuth atoms is responsible for the observed spin reorientation transition at 90 Kelvin. In our knowledge, very few theoretical works have been done on the magnetic anisotropy for manganese bismuth thin film. So the goal of the work is to study structural, electronics, magnetic and anisotropic properties for manganese bismuth, oxygen attached on manganese bismuth, tantalum attached on manganese bismuth, and oxygen attached on the bilayer tantane on MnBi bismuth system using the DFT calculation. So in this work, we did the magnetic properties of manganese bismuth 001 surface 10 film terminated with manganese atom. Then we studied the absorption effect of oxygen and tantane atom on the magnetic properties of MnBi films. And then the effect of oxygen on the magnetic properties of tantane capping manganese bismuth 10 films. And we will end up with the anisotropy magnetic properties for manganese bismuth, oxygen manganese bismuth, tantane on manganese bismuth, and oxygen on the bilayer tantane manganese bismuth system. Okay, let's talk about first theorem approach. The magnetic anisotropy contains two different effects. The long-range magnetic dipolar-dipole interaction, which leads to the so-called sharp anisotropy. And the second one, the magnetocrystalline anisotropy energy, originate from the spin-orbit coupling. The last part is a quantum effect that breaks the rotational invariance with respect to the spin quantization axis. The value of MnAI per atom is extremely small in bulk, but can get much large in nanostructures due to reduced dimensionality. From the theoretical point of view, there are two different methods to MnAI calculation. The first one is the fully relativistic self-consistent field calculation. And the second one is the first theorem approach. Accessing the MnAI for systems containing hundreds of atoms by the former approach is especially challenging, since it requires a well-converged charge density as well as a consuming computation time. In the latest method, the MnAI is given by the bond energy difference obtained after a one-step diagonalization of the full Hamiltonian, including spin-orbit coupling, starting from the self-consistent scalar relativity density potential. This approach is not only computationally efficient, but also numerically very stable, since the self-consistent effect with spin-orbit coupling could be ignored. The MEA in a very good approximation is calculated by using the force theorem approach. A self-constant field collinear calculation without spin orbit coupling is done, followed by the rotation of the density matrix in the right spin direction. And a non-self-constant field non-collinear calculation with spin orbit coupling is performed. The MEE is obtained as the difference of the bond energy between two spin moment direction 1 and 2. So in quantum expresso, the first theorem is implemented in two-step way. Like say before. So the self-constant calculation with scalar relativity pseudo-potential without spin orbit coupling is performed to obtain the convergent density and the spin moment distribution in real space. And spin moment is globally rotated to the certain direction, followed by a non-self-constant calculation with full relativistic pseudo-potential with spin orbit calculation. The change of bond energy between two spin moment direction gives the total MEE. The total MEE is the composite over the different atoms I in the slightly different way. So MIE equal the integration of the energy multiplied by the density integrated over the energy. So we have the difference between the two state spin, where the Fermi level of one of the magnetic configuration is subtracted under integrals, and exact Fermi level for two configurations are used as the limit of the integration. Due to the total charge conservation in this canonical approach, the sum of the MEA over all atoms gives exactly the total MAE. Then move to the computational method. So in bulk system, manganese bismuth has a hexagonal compact structure. The external functional we use is the JJR PBE. The lattice parameter is A equal 4.226 angstrom and C equal 6.211 angstrom that we obtain by minimization of the energy. The pseudo-potential type is for Vanderbilt ultrasoft. And the cutoff energy was 4.5 Rydberg. And the key point sample was 775. We use the supercell technique to build our multi-layer MBI systems. The exchange functional was the same JJR PBE. And the pseudo-potential type is a Vanderbilt ultra soft. And we use the in-plane parameter A equal 4.26 angstrom. The cutoff was the same for 5 rigmet. The sample of key point 771, and the vacuum space for about 12 angstrom. We consider 7 adsorption sites. B1 and B2 are the 1 and 2 fold bridge site. T, the top site. ASTP and FCC are the 3-fold hollow atomic site. And we also consider 2 relaxed sites, R1 and R2. This is to prevent the oxidation effect. The bismuth atom in dashed red circle is located at the sublayer. Then let us talk about result and discussion. So in this slide, we present you a result about the relaxation of MnBi 10 film made of 11 layers. So we relax all of atom. So we relax all of atom by fixate only the 4 bottom atom. So in this table 1, we present interplane distance in angstrom and magnetic moment in μB for the outmost Mn and MnBi plane for MnBi system. As you can see, manganese layer exhibit the ferromagnetic coupling, whereas MnBi and manganese atom exhibit the antiferromagnetic coupling. Let's move to the absorption energy for oxygen and tantalum atom on manganese bismuth. So in this table 2, we display the absorption energy in μB for oxygen on MnBi and tantalum sur MnDi in the ferromagnetic coupling. The ferromagnetic coupling here is the ferromagnetic between manganese layers. So by exploring the 7 absorption sites, The preferential absorption site for oxygen on manganese bismuth is a bridge 1 with the absorption energy of -6.7, whereas for tantalum on manganese bismuth is FCC1 with the energy absorption of -5.67 EV. This result shows that we have the subsorption effect. Here we are showing you the result about the relaxation and magnetic moment per atom for the two systems, oxygen and tantalum, on MnBi systems. So we can see here that oxygen atom is located from the MnBi system at 0 to 22 angstrom with the magnetic moment, with the induced magnetic moment of about 0.07. In the case of tantalum, we have the antiferromagnetic induced moment for about 0.92. Let's move on our main result concerning anisotropy property for MnBi-free system. Oxygen adsorbs on manganese MnBi, tantalum on manganese MnBi, and oxygen on Theia MnBi system. Okay, so the MAE property was calculated using Forster calculation. And the negative value means that the orientation of the magnetization is perpendicular from the films. But when we obtain the positive value, the magnetization is oriented in the plane. So, for the free MnBi system, we obtain the value 0.35. So this value means that the magnetization is in plane. So this is in agreement with Wu et al., but at variance with Sun et al. But when oxygen is adsorbed on MnBi, we have the switch of the magnetization from the plane to the outer plane. So we obtain the value 3.98. About tantan on MBI, we observe that the in-plane magnetization is reinforced. So we obtain 3.94 millieV. But when we absorb oxygen on tantan capping layer on manganese bismuth, we have the in-plane. So the presence of oxygen doesn't modify the orientation of the magnetization. We have the reinforcement of the MAE.
Brice, you have just 1 minute left.
So in conclusion,
Then we'll take
the
questions.
MnBi with and without the capping TIA layer exhibit both in plane magnetization. The presence of oxygen atom on MnBi slab reorients the ME from parallel to perpendicular magnetization. While adding oxygen layer on tantan MnBi system, the oxidation effect does not modify the Mn orientation when MnBi film is protecting. So we would like to thank the organizer to have allowed us to present our work, and computational work, computational resource when provided by CHPC from South Africa. The collaborator of the work was Mukila and Mabiala Poiti from Mireille University, and Raji from College of Science, Energy and Technology from South Africa. Thanks for your attention.
Okay. Thank you very much, Brice. Thank you very much.
Thank you.
Yeah. So we will take questions now for 5 minutes, and then we'll take a break afterwards. Okay. Does anybody have questions for Professor Brice?
I sent a question to the chat. He mentioned the use of the, Brice, you mentioned the use of the FT plus U in the beginning, but you didn't say more about it. You didn't say much about it.
Yeah, this is a good question. So we did not use DFT plus U. We use a simple DFT.
No, but at the beginning you said something about LSDA plus U. Oh, that was other people's work, right?
No, at the beginning, I say that there is an author who used DFT plus U.
LSDA plus U, okay. Okay, but you did not use LSDA plus U, no.
So maybe we can try to use DFT plus U to see what we can have.
Okay.
When using U-bar approach.
Yeah, but the U parameters will just be on the transition metals, right? Manganese, tantalum, right?
Yeah.
Manganese, yes.
Okay.
And manganese, maybe, yeah.
So how do you think this will change? Because, for instance, when you don't put anything on the material, like, can you go 2 slides before this one?
Excuse me?
Can you go 2 slides before this one? Yeah, this
here.
Oh. No, yeah,
okay.
Yeah. So you see the MAE for when you don't put anything on it, the pure manganese bismuth thing is 0.35, right?
0.3, yeah, okay.
Yeah, but if you add U to it, it will change because 0.35 is small. So if you add U to it, DFT plus U, it's probably change in one way, maybe increase, or I don't know. So it's good to add U to see what you will get. For the other ones, I'm not sure the change will be great. I don't know. But adding U to it, then for the best system, then this can be helpful. So let me ask you this question. So the oxygen you add, so you just add a single oxygen atom, or so it's not the oxygen molecule, it's the oxygen atom, right?
No, it is an oxygen atom.
Okay. So you just add one to the whole surface, to the whole layer?
Yeah, so we add the oxygen by changing the adsorption site. So here we consider the lowest considering site.
Okay. But in real life, don't you think it should be the oxygen molecule, not the oxygen atom?
But it is not, it is just it is one way to see the thing. We are calculated for the molecular oxygen atom.
Okay. Okay. Thank you. Any other questions for Brice? Yeah. Any other questions for Brice?
I have a question.
Yes, Richard.
Yeah.
Richard, sorry.
Brice, about the force theorem, that makes the calculations much faster. Is that correct?
Can you repeat, please?
Does the force theorem make the calculations much faster?
Yeah, it is faster than doing the fully relativity calculation.
So then a question about the force theorem. Is that the same idea that OK. Anderson has used for other properties like displacing atoms or pressure, or things like that?
Excuse me, Professor, I did not understand. Yeah.
Okay. In your calculation, where you had you showed us the difference in two energies.
Yeah.
And there was a density of states for and energies for each one, and you integrated up to the Fermi energy.
Yes. Okay. Yeah.
Then if I understand right, what you did was to do a calculation with a charge density that was derived from one calculation, and then use it in the to get that energy difference, the same charge density. Is that correct?
So what we did is that we calculated. So we do the self-consistent calculation for our system in the collinear approach.
Yes.
Then we do bond calculation by using relativistic pseudo potential.
Okay.
So including spin orbit coupling by orienting for one configuration, the magnetization along Z-axis, and the second one along the surface plane. And then we did the difference between these two results to obtain the MEA.
Okay, that is very nice that you can do that. And is there a general reference for what you call the force theorem?
Yeah, the reference is, I give the reference, yeah, sorry. Okay. So, okay. Let me.
Oh, it's Antropov.
Yeah.
Okay. Mm-hmm.
I apologize for
No,
not
it's
really
not
seeing-
Antropov. No.
Oh,
The first theorem is done by Leal.
oh, okay, then I did not notice that. So
What's the name?
that's
I
the
don't
only
see it.
thing then finally I would like to point out is that I think that idea has been used in several different contexts, and it's very nice that you can use it for the magnetization and the magnetization anisotropy. Thank you.
Okay. Yeah. Okay.
Okay, thank you.
Yeah. Thank you very much, Brice. So if you have other questions, then we'll have a session about in 50 minutes time, and you can ask Brice more questions there. So you'll be in one of the rooms and you can ask more questions there. Actually, we should go on to the next session now, but let's take 2 minutes to stand up and stretch while Steve, our next speaker, shares his slide. So Brice, please don't share. Thank you. And then Steve, our next speaker.
Okay, thank you, Mololo.
Yeah. Thank you very much, Brice. We are happy you could join us.
Thank you.
Yeah. Before Steve talks, take 2 minutes to stand up, stretch yourself, turn your neck, get a cup of water, and then Steve will start in 2 minutes. Steve, you're supposed to stand up and stretch.
I'm stretching, I'm standing. Can't you see? I'm stretching on my chair.
Okay. Thanks a lot, Amy.
Morning.
Morning.
Okay. So I think we can start now.
Okay.
Okay, so good day, everybody. So our next speaker is Dr. Stephen Ndéngue, who is here at the East African Institute for Fundamental Research. So we'll be talking to us about simulation of the water dimer. Okay. So over to you, Steve.
Okay. Good. Hello, everyone. I'm, like Omololo said, I'm Steve Ndéngue. I'm a faculty at the East African Institute for Fundamental Research. And I'm glad to have this opportunity to show some of the work that we've been doing. Like in our group, we are particularly interested in understanding quantum effects, both in the gas phase and in the condensed phase. So this session is about molecules. I'm going to talk in this specific case about a molecule in the gas phase, specifically a clustered water dimer. And how did we start this project? How did we get to work on this specific project? About a year ago, a group in China were able to build a very nice free electron laser that they were hoping could help get very accurate spectra of various type of cluster, and quite naturally they start on the water dimer, which had some debate for several decades now. And initially we didn't know about, so they were able to record the spectrum that is shown on the figure here. And they made also some calculation that I would call for now low quality calculation to be able to assign all the various features that you can see on the spectrum. So these are the spectra that they obtain, and these are the various results from the calculation that they were able to do. Like, as you see, they did some MP2, CCSDT calculation to be able to address all of the various features that you see on the spectrum. However, they were not quite happy about the agreement between the theory and the calculation, and they contacted one of my colleagues to ask if there's a possibility of do better calculation so that experiments and theory match a little better. So that's how I got into this project, and they were really interested in matching not only the experiment, but also understanding those three features that you see on the A band that is displayed here. So we started working on the project, but before there's this question, why is the water dimer interesting? First of all, water dimer is the smallest, simplest water cluster, just 2 water molecules. And there's this idea that if one is able to understand the hydrogen bonding on these choose in this simple system, there's a chance that we understand a little better the hydrogen bond in liquid water. Another reason is the fact that some people claim they have observed the water dimer in the atmosphere, and for that reason, people believe that it also plays a role in the Earth's energetic budget through absorption of solar radiation. So this is still a question that many people are investigating and trying to understand whether or not the water dimer plays a role into that specific part. In our case, we are really interested on that system on the fundamental viewpoint. By fundamental viewpoint, I mean that we want to know how to obtain accurately the infrared spectrum of the water dimer, but also what is the origin, what type of motion each of the features, each of the bands that you observe in the spectrum, where do they come from? So going through the literature, we realized that a lot of work has been done on this system, and here I mainly point out a few experimental results. And this year, like this type of work are quite recent. There is a lot of interest in this molecule recently for various reasons. So there was this viewpoint that was published in Journal of Physical Chemistry later this year that was somehow replied to the paper from last year. They made some experiment and they claimed that the spectrum or the assignment that was made on this spectrum is partially wrong. Namely, those 2 features that were expressed here are the ones that are displayed here. And that's the main assignment that has been done for several decades now for this system. But there was this specific experimental result that we obtained a few years ago which seem to contradict on the assignment of those two features. In particular, this feature around 3550 wave number seems to belong to the water trimer and not the water dimer. So there is a lot more that it is to learn on this specific system, and we decided then to work on this problem. I don't want to go into too much detail because of time, but basically there are not too many computational methods or theoretical methods that can describe very accurately the spectrum of the water dimer through computation, and not only the spectrum, but predict also the origin of all of these features that are observed here. The method that we are using, and I'm going to talk briefly about it, is one of these methods, one of the few methods that allow to do it quite efficiently, and also to say specifically where does each of these features come from. And therefore, we hope that we should be able to provide some additional data, some additional information to resolve that kind of debate that has been going on for a few years. So how do we start? How do we approach the problem? We start from scratch, like from the molecular Hamiltonian. You have the molecular Hamiltonian. If you apply the Born-Oppenheimer approximation, you're able to separate the motion of the electron and the nuclei. And solving the motion for the electron, you get the energy. So there are various ways to do it. You can do it using DFT. So this is actually more or less the only slide that talks about electronic structure. So you can do it using DFT, but you can also use a more accurate method. Those are coupled cluster, single and double post-Hartree-Fock methods to solve this type of problem. And this is what was done for the specific work, and the specific result I will be presenting. In addition to, so once you obtain this electronic energy, usually you feed them into what is known as the potential energy surface. The potential energy surface is more or less a conceptual surface within which the nuclei, the ions are moving. And this motion generates all the properties one is interested in, the infrared spectrum or any other property that one is looking for. For the infrared spectrum, in addition to the potential energy surface, we also need the dipole moment. The dipole moment gives you the intensity of all of the peaks that you observe in the spectrum. So all of these, whether it's the potential energy surface, whether it's the dipole moment, are all obtained through electronic structure, quantum chemistry calculation. So for our work, we used the surfaces that were built in China. The surface and the dipole moment surface was built in China, and they were of decent quality. So after that, after we have the potential energy surface, we have to do the dynamics. In this way, again, we go the full quantum way, and we decide to solve the time-dependent Schrödinger equation. We are able to do that because the system we are dealing with is not particularly big, though I would like to put big in quotes for a reason I will show you later. So the method that we are using is called a multi-configuration time-dependent Hartree, MCTDH. Some people may know about it, others don't. It's a time-dependent version of the MCSCF method for those who are well-versed in quantum chemistry. So more or less the idea is the following. You have your wave function, wave packet, time-dependent wave packet that you want to follow through time, and you express that wave packet in a time-dependent basis. So each time step, as the wave packet is moving, the basis onto which it's expressed is optimized. In the end, you have a set of equation of motion, but better, you have a motion that is very smartly defined, so that you are able to save a lot of memory by just selecting a very localized basis throughout the motion of your system. One example of this kind, one clear way where you show that this method is appropriate is if you were to solve this problem head on, like without thinking too much. For a system that has like 9 degrees of freedom, this is a molecule like methane, for instance, the amount of memory you will need for quantum calculation will be close to 1.5 petabyte. Using the method that we are using, you use just about 7 gigabytes. So it's a significantly gain in memory, and that transfer into a gain in time. And this is particularly important in the idea of mitigating what is known as the curse of dimensionality. Shortly, the curse of dimensionality is one issue that occurs when we try to solve a problem fully quantum mechanically, and in particular in quantum dynamics. As the number of atoms in your system increase, the number of degrees of freedom increase, but in an exponential way, so that quickly you are unable to solve this problem even on a cluster, because the amount of memory that is required is way too large. So once we have our method to perform the propagation, we have our potential energy surface, we can start producing various absorption spectra and start analyzing the result. So how do we do that? The first thing we have to do is to prepare an initial wave function, which is usually the ground initial wave function of our system. We apply the dipole moment to be able to get the proper intensity. And then you propagate your wave packet on potential energy surface. After some time, you can record the autocorrelation function whose Fourier transform will give you the spectrum like you can see here. So this is a result from our propagation, and you can compare this with the experimental data that we were actually trying to match from the start. So immediately you can see that the set of features seem to appear both in the experimental spectrum and the theoretical spectrum. So there are some similarities, but there are also some significant difference. For instance, the peak around 3600 also seem to appear in the experimental spectrum, and several peaks around a little above 3700 also seem to be present in the experimental spectrum. What, on the other case, we don't see is that we don't see anything around 3550, but we see on the simulated spectrum some specific feature around 3650 that does not appear at all in the experimental spectrum. Also, there is this set of feature and the double peak that we see here, and I'm going to talk a little bit about that. So we get this spectrum in the end, but the question is, what are the origin of those peaks? What do I mean by origin? What type of motion is displayed here? You have two water molecule. Is it the motion between this hydrogen atom between the two molecules? Is it this free hydrogen atom? How do we get that information? Well, the benefit of using the type of method we are using is that we can perform some kind of artificial excitation on each of the water molecules. So you can excite, for instance, this OH bond, try to elongate a little bit the hydrogen atom, and generate an initial wave function that looks like that one, do a propagation and see the type of feature, type of signal that we obtain in the propagation. And that if that signal matches the experimental, this theoretical signal, we can claim that, okay, this specific feature that we observe in the theoretical spectrum matches the one that we have here. For instance, this purple feature that is observed here at around 3600 is precisely the donor OH stretch. So it's the motion between this hydrogen atom along this direction. So the donor has the possibility of extending. And at the same time, the small feature that we see here is clearly present here, and it corresponds to the symmetric stretch of the acceptor. So overall, most of the peaks, or at least the 4 peaks that are defined from the experimental data, we are able to give a proper assignment. You can say specifically this specific feature belongs to this part and that other part. What is missing actually from our treatment? So here overall, we are able to identify 4 peaks. I don't have time, but I can say a little more about it later in the discussion. But what we actually can see, what we actually don't have from this simple picture are those doublets that are shown here and this very last peak. But we've done a lot more work in between, and we have some kind of explanation as to the origin of this specific feature, but I'm not going to go into that, and I'm just going to jump to the conclusion. So we can talk about that a little more later if you're interested. So overall, we have a method to study this type of cluster in full dimensionality, but not only study those clusters, but also identify various features that are observed on those in the simulated spectrum. So this is not actually new. This type of method, this MCTDH approach has been done for some time now. For example, they were able to unravel the feature that are observed on the Zundel cation and many other systems in Germany. And what we are trying to do right now, because this is a work in progress, is those are kind of preliminary results. What we are doing right now is trying to understand the very last features that I shown you at the bottom end. We have an idea what it is, but we need some simulation to confirm that assignment to us. And this is where I'm going to end my talk, and I would like to thank a few people. So there is Hans-Dieter Meyer, which is the principal author of that MCTDH code, and they are the group in China who provided the potential energy surface and dipole moment. Thank also the institutional support from ICTP, Government of Rwanda, University of Rwanda. and our institute here in Kigali. And finally, I would like to do some little advertisement. So we'll have a PhD and postdoc position opening this fall. This is a project that is supported by EPFL and University Mohammed VI in Morocco. And the work will be around the topic of photocatalysis. So this will be announced on the website of our institute later on, maybe next week. And if you have any interest in this type of question, this type of research, you should feel free to email us. So I'm going to end now, and thank you for your kind attention.
Okay, thank you very much, Steve. Okay, we'll take questions after we take all the short talks. So the next short talk will be by Mireille. I don't know if she's around. If she's not around, we'll go on to, is she here?
No, it's not Mireille. I think it's Prof. Pedersen.
Oh, sorry. Yeah, sorry. Yeah, the next talk is by Mark Pedersen. Sorry. So Mark, please. Okay, Mark. Thank you very much, Mark. So Mark Pedersen from the University of Texas at El Paso will be giving us a talk on molecular magnetism and quantum. No, he's from the Molecular Magnetism and Quantum Theory Lab. He'll be talking to us about molecular magnets. Okay, Mark, please. Thank you.
Okay, thank you very much for the nice introduction. My name's Mark Pedersen, and I really enjoyed the first two talks because I'll be talking about manganese and magnetism, and the particular molecule I'll be talking about is affected strongly by waters in close proximity in several different ways. And so what I wanted to do was just give a very brief overview of some of the challenges that one needs to address when looking at magnetism in molecules, and give you a couple examples of two different effects that arise from the spin-orbit interaction. And then I'll tell you a little bit about some work that's just been going on in the last year or two from several members of my group. So molecular magnets were actually discovered accidentally by a person who was Christo and Lise, who was trying to make a model for a water splitting complex, the oxygen evolving complex, and they ended up with this molecular magnet instead. It had some very interesting quantum tunneling and magnetization properties, which sort of started the field of molecular magnetism. And I got interested in it just from the standpoint of electronic structure and thought it was a good challenge to electronic structure methods. So the two types of quantum behavior that occur from the collection of 1,000 electrons in 100 atoms go by the name of resonant tunneling of magnetization and Berry's phase oscillation. And then there's a second type of idealized molecular magnet where exchange coupling between different metal centers is important. And that was sort of the picture that we liked for many years. And now as the experiments get more sophisticated and as we're able to do much more complicated calculations, we're starting to see both of those phenomena occur in certain molecular magnets. And that might be important from the standpoint of designing qubits, because if you want to make a system out of spins that for a quantum computer, you want to be able to say both how that system is going to behave ideally and how it's going to behave in reality. So let me get my pointer here. And also go to the next slide. Okay, so the electronic structure method that we use is some work that I did at the Naval Research Lab for many years. It's based on Gaussian type orbitals instead of plane waves. And everything I'll be talking about today is an isolated system. The important point for today, and it was alluded to significantly in the first talk, is that we always talk about spin up and spin down electrons, but in fact, even once we agree that there's two flavors of electrons, we have to decide which way up is. And so what it means is that relative to the molecular geometry, we could define up as out of the page and down as into the page, or we could define up as right and down as left. And when we start putting in the spin-orbit interaction, that definition actually matters, and the energy changes to higher order depending on which axis of quantization we chose. And we heard some discussion about the force theorem, and that's one of the ways that one can calculate these energy differences due to your definition of which way's up and which way's down. Okay, we use a numerical method to calculate our integrals, and I just kind of pictorially show that in this cube for benzene. Okay, so again, the first molecule where resonant tunneling and magnetization was observed is this manganese 12 acetate molecule. It's ferrimagnetically ordered. It has 8 s=2 electrons on 8 s=2 centers on the outside, 4 s=3/2 centers on the inside. And because of this phenomenon where you get level crossing due to the anisotropy Hamiltonian, you can measure the barrier very accurately by applying magnetic fields that are tuned to the anisotropy parameter D. And both experiment and theory agree that it's on the order of 0.55 Kelvin, which in this case means the magnetism barrier is 55 Kelvin, and these are very long-lived systems. Okay, so I said that there were two types of systems. The most classical one, if you will, is a molecular magnet. They tend to be composed of large local spins. You can think of the exchange coupling between different spins as effectively being infinite. And because of that, the lowest excitations in the problem are due to all the electrons flipping their spins simultaneously. That would be a zero energy excitation if there was no such thing as spin orbit coupling. And again, it's resonant tunneling and magnetization and Berry phase oscillations that occur in this case. I would say that this example is a case where we should expect single determinamental methods such as DFT to work very well, and it does. The other type is when you have small spins, which would mean that the lowest excitation in the problem was one electron doing a somersault on its site. And if in the zero overlap limit, that would be a zero energy excitation. And for these systems, they're intrinsically multi-configurational, and you need to map them onto a Heisenberg Hamiltonian or something of that nature in order to describe them. But DFT seems to be the best way to approach these systems. Okay, so recently there was a group in Europe that confirmed what's known as the magnetoelectric effect in this iron 3 molecular magnet, and I show it here on the left. And so I did some work on that with my colleagues in Sweden, Carlo Canali and Folker Islam, and an undergraduate student, Alexander Johnson, who's here at UTEP now. And there had been some questions about why there were two different size dipole moments forming. And we think we've determined that it's because, in fact, it's multiferroic. You can have the Hund's rule ground state, which is spin 5/2 on each one of these triangular vertices, or you can have a double spin flip and have S=1/2 low energy states. And so as a result, we think this qubit here is going to be sensitive to magnetic fields, electric fields, pressure, and temperature. And I just put this question down here for you, Coulomb corrections. We know that density functional tends to overemphasize the size of a d electron. That makes the J's increase. And that's been shown by many, many groups. And so we can imagine that if we were to correct for that result, we might get smaller exchange coupling. Okay, so then two other things we've worked on very recently are this manganese 3 monomer. It dimerizes. And what we found was that when you break it apart and chemically stabilize it, you get S=1 centers instead of S=2 centers. So that's, again, another violation of Hund's rule as we're taught it. And when Zara discovered this, I thought there must be a bug in my code, which bothered me. But then we started looking around and found that Haipeng Cheng, Sam Trickey, John Stanton had found other S=1 states, as had Jorgen Schnack, and also found even S=0 states. All of these systems violate Hund's rule. But that led us back to manganese 12 acetate, and this is some work that's done by Karma Dama in our group. And we decided that if we can get these S=1 spin flip excitons in other manganese centers, that possibly this most studied molecular magnet, the one that started the field, might also have these low energy excitations. And sure enough, it turns out that regular old DFT, no corrections, predicts that you can have these spin flip excitons that occur on each of the outer 8 manganese. They're very forbidden. They're spin forbidden, they're dipole forbidden, and they're Frank-Condon forbidden. And the reason they're Frank-Condon forbidden is because the water metal distance changes by an amount that's very large compared to the vibrational Debye-Waller factor or whatever it is associated with the waters moving above the manganese. And so we're working with Jan Musfeld, an experimentalist, to use vibrational characterization, such as we heard from last talk, to see if we can actually confirm the presence of these long-lived excitons in this molecular magnet. It's important to understand because they really change the magnetic anisotropy. They reduce it from this relatively large value of 55 Kelvin to about 10 Kelvin. And so there again, by understanding these things, we might be able to make quantum devices that switch when you get these low-lying excitations. So with that, I just want to point out that in the field of molecular magnetism, this problem that we often correct from Hubbard-U approximations occurs in different ways. It overestimates spin excitations. It causes problems when you get the wrong charge transfer between the substrate and the active magnet. And it also affects spin-dependent electron transport because you don't have an initial and a final state due to this self-interaction error. And so the other area that we're working on in our group is trying to put in this new self-interaction correction, which we refer to as Fermi-Lovedean orbital self-interaction correction. Very briefly, it's a way of putting unitary invariance into self-interaction correction in a very similar way than, as a solution to the same problem that existed in the Hubbard-U methodology at the time that Anisimov kind of solved that and have rotationally invariant Hubbard-U. So I think this is an empirical approach or a non-empirical approach to self-interaction corrections that might be useful in a variety of fields in the future. And with that, I'll thank the organizers again for organizing such a great conference. Where we're going in the future is time-dependent spin electric coupling, and that involves putting in all interactions between spins, electrons, and photons. Thank you.
Okay. Thank you very much, Mark, for the enlightening talk. We will take questions at the end of when everybody has spoken.
Okay.
Another thing, actually, Mark and Steve have their posters online. So, yeah, Mark and Steve and Gamachis, they have their posters online. So you don't have to write too much. You could, some of the references you need are on the slides, and it will be good if you take a look at them. Okay. So we'll move on to the next person, who is Mireille Kabuyi Bilonda. So Mireille, please share your screen, and you have 10 minutes. So you should share your screen.
Share screen. Good morning, everybody. Do you hear me?
Yeah, good morning.
Good morning.
Good morning, yeah. So you can share your, yeah, good.
Can see it?
Yes, we can see your screen. Computational study of mbandakamine A, dimeric, yeah. So put it in slideshow mode.
Yes. Yes. Come here.
Slideshow? No. There's slideshow on top. No, there's slideshow mode on top. No, no, to the right. You see slideshow? Yes.
Yeah. I don't know. It doesn't work.
No, click on slide and then choose an option. Start from this slide or start from the first slide.
It's not highlighted. That's the problem. Or I do have it.
Highlighted.
It's not highlighted.
Yeah. Okay. Yeah.
Recording started.
No, but go there to slideshow. Oh, it's not highlighted. Ick.
I don't know what is happening.
Okay, I understand. Does anybody know what to do? I have no.
I think we can all see the slides clearly enough if you just want to click through them as it is.
Okay, yeah. So you can click through the slides, yeah?
Yeah, because I did open it before and then
you can press F5.
Yeah.
Yes, F5, I did.
But it doesn't work. It's not highlighted.
I don't know if okay.
So let's
start with escape.
Okay. Good day, everyone.
Yeah. So let's continue.
It's a pleasure to. Yeah. It's
do one thing on the right. Remove the bar on the right. Right click. Kill the bar on the right with properties and everything. It's distracting. Huh? Or you can click the little arrow to move it.
I think
the bar on the right.
Now.
Okay.
Is it fine? Everyone can see it.
Yeah, you can see. So I think you can start.
Okay. Okay. So as I was saying, it is a pleasure to be with you this afternoon. So I will be presenting my studies on computational study of mbandakamine A dimeric naphtylisoqinoline alkaloid with antimalarial activity. So malaria is a serious problem in the world.
You need to progress your slide by clicking on the left.
Yeah. Okay. And it is a serious world problem, and it is caused by the infection of malaria of a.
No, you need to click on the left because we don't see. We still see the first slide.
You still see the first slide.
Yeah. So click on the left where you have the slides listed.
it okay?
Or maybe on the
Because
other one.
from my side, I can see the second slide.
Oh, I don't know. Can everybody see the second slide? I can only see the first.
I think it's probably jammed. Could you unshare and reshare again?
Okay.
You share?
Yeah, click stop sharing and then share again. Ah, that works. Perfect.
Oh, perfect. Yeah, thanks.
Okay.
Thanks,
Good.
Sinead.
Yeah, also
Okay.
in introduction, I was saying malaria is a serious world problem, and it's caused by an infection of mosquito, most probably with the Plasmodium falciparum, which is the most dangerous species. So it causes about 2 million cases per year and about 400,000 deaths. And in Africa, almost 80% of malaria, and the person which are in risk are children and pregnant women. So every 2 minutes, there's a children who died with malaria. And the main problem is the resistance to new drugs due to this plasmodium, and we have to come up with a new drugs which at least keep the peace of the growing of the resisting of the drug. So to do that, we need to access new compound, which new mode of action, and this can be found from natural product, which is a potential source of new drugs. So as my natural product, or yes, is mbandakamine A, which is a naphtylisoqinoline alkaloid isolated from the leaves of Congolese and Australian species. This molecule has confirmed antimalarial activity. It has a dimeric structure which has 2 units and 2 asymmetrical cap central BRI axis. And each unit consists of a naphthalene moieties and anisotropy moieties. And those moieties are connected by equilateral axis. It can have intramolecular hydrogen bond, which make this molecule computationally interesting to study. So here I have the molecules presentation. So we have performed the conformational preferences and the computable molecular properties of this molecule in different media, in gas phase and in 3 solvents, which are chloroform, acetonitrile, and water. And as the computational method, we have done calculation in vacuum utilizing the Atrifork and the GFT method. And in solution, we have also used a PCM model, and calculation in solution we performed as a single point calculation on the molecules. As software, we have used Gaussian 0-3 for visualization, Cosue, and Camcraft. As a result, we have found that the conformation preferences, especially the stability, are influenced by the presence of the intramolecular hydrogen bond which this molecule was having, the visual orientation of those 4 moieties. And an additional factor was also the presence of a stacking interaction with this molecule. I can show them in some molecule after. And we have found different type of hydrogen bonds. So this molecule was having many type of hydrogen bonds. So we have found between the moieties, between the naphthalene moieties, between the isoquinoline moieties, between the isoquinoline and the naphthalene moieties, and so on. So there are some hydrogen patterns. So from this one, it has a nitrogen bond between, this is the naphthalene moieties. So it has a nitrogen bond in the naphthalene moieties. This is anisotropy moieties. So this one have a nitrogen bond in anisotropy moieties. This one is a OH pi interaction between the isoquinoline moieties and the naphthalene moieties. This one have an nitrogen bond between the naphthalene moieties and the isoquinoline moieties. So this is just some example I just choose to show those hydrogen bonds. So we also evaluated the relative energy of this molecule in different media. So in solution, in acetonitrile, in vacuum, in acetonitrile, chloroform, and water. So we find that the relative energy was decreasing with the increase of the polarity. So we find that in the water, it was having a low relative energy. We have also investigated the dipole moment for different conformer, and we found that for the dipole moment, it was increasing with the polarity of the solvent. As you can see, in the red, the water solute was increasing. For the homolumo, it was also the energy cap was also increasing with the polarity. So we have also evaluated the energy of the solvation to see the effect of the solvent, and we find that it was negative in chloroform and acetonitrile, but it may be positive in some, positive or negative in water. That's what we did found for the delta J solvation. And as conclusion, I can say that we find that the presence of the hydrogen bond lower the energy conformer and the mutual orientation of the four moieties. The conformation preferences of this molecule are determined by the presence of the hydrogen bond and its patterns, which have a dominant factor. The intramolecular hydrogen bond also have an influence on the dipole moment, homolumo energy, and the solvent effect was positive in chloroform, acetonitrile, but may be negative or positive with value in acetonitrile in chloroform. And thank you. That was my small talk.
Okay. Thank you very much, Mireille. Thank you. Again, we'll take questions afterwards. So the last of the 4 talks we have today is by Gamachis. Yeah. We'll take questions afterwards. So Gamachis, Mireille, if you stop sharing, and then Gamachis can talk for 10 minutes. Thank you very much, Mireille.
You're welcome.
Okay, so put in slideshow mode and then we start. Okay.
Shall I start now?
Yes, Gamachis. So you start and talk to us about lithium-ion batteries. Thank you.
Sure. Okay. Hello, everyone. This talk is from Addis Ababa University, Ethiopia. This is our group photo with some group members. As you can see from left to right, those who are standing is the first one is Dr. Groom, Dr. Chorinet, Dr. Edilfana, our group leader, and Mr. Nagash. Those sitting, Getachew, Freu, Masfin, Henok, and myself. So I would like to really acknowledge the organizers for this chance. Are you hearing me, please? Hello?
Yes, we can hear you and it's fine.
Yeah. So we have been successfully communicating with US senior physicists using this opportunity. I mean, using the March and the June meeting. We have already got 2 collaborations from USA. The first project is now active. The second project is just we are now developing joint proposals, and also we are communicating well with others to come up with a concrete project. So we are grateful for the great job you are doing. Thank you. Really, I would like to mention Omolulu and Ami, because they are updating us whenever we miss some information. Thank you for that. Now.
Yeah, and Richard and Professor Renata and Steve and Sinead.
Okay.
Okay, go ahead.
Thank you, Omolulu. Yeah. So now I want to talk on past 3D lithium-ion diffusion and the high electronic conductivity of lithium manganese silicate surfaces for rechargeable lithium-ion batteries. As you can see from the figure, this is a crystal structure of lithium manganese silicate. The figure, you can see the unit cell, which consists of manganese, silicon, lithium, and the oxygen. And you can see from the right side, B, the supercell 2 by 2 by 2. On the bottom, you can see the polyhedral form of what already indicated in A. So all the cations, manganese, silicon, lithium, are rotated by 4 oxygens. So you can see, for example, the manganese, which is rotated by 4 oxygens. So in principle, there might be some distortion, as Mark has just now lectured. I mean, raise the idea of this one in his presentation. I mean, there might be something like Jahan-Taylor distortion, Jahan-Taylor effective distortion actually. So I will talk after a few slides about this one. So you may wonder why this guy is talking about this lithium manganese silicate of this, I mean, this cathode material. You know, this is it has high theoretical capacity, high thermal stability due to this strong bond between this silicon and the oxygen. So it makes the system very stable thermally. The other is low cost of production, environmental friendliness. So, however, there are, as usual, some drawbacks in these materials. For instance, it has a very low ionic diffusion to the order of -18, pure electronic conductivity to the order of -16. So, our task is how to make these materials. As you can, it is bulk insulator. So our task is how to make this compound or this material conductor. So our strategy is just surface crystal structural design. To do that, we use DFT plus U, and the GPAW code is our choice. So as you can see, what we did is we checked the structural stability of these materials. In order to do that one, we did surface free energy of some selected surfaces of these materials. As you can see from the table, orientation 1, 0, 0, 0, 1, 0, 0, 0, 1, 2, 1, 0. You can see here very clearly the surface energy of the material is almost fine, but we prefer 0, 0, 1 surfaces because, as you can see from Wolf constructed equilibrium shape, 0, 0, 1 has higher coverage. So practically, the other phases, for example, the most stable one, let me say, I mean this 210 might be covered by other surfaces. So 001 has higher surface area, so it is active electrochemically, both kinetically and thermodynamically. So we choose 001 on the right side, you can see the crystal structure, there's all the surfaces, I mean, all the surfaces. So the challenge is how to, as I said, it is bulk insulator. The material is bulk insulator. So we have challenged how to make the material, how to use, because the DFT underestimate the band gap when we wanted to study the electronic structure of this material. So we have to fix the U value. I mean, we have to use the DFT plus U. In order to do this one, we calculated the band gap of the material as a function of U parameter. So we fix it at 3 electrovolt, in which our calculated band gap is 3.42. You can see from A, our partial density of state. At GGA, I mean at DFT, it underestimated the band gap is underestimated. When you come to B, when we add the U value, the band gap is calculated to be 3.42, which agreed well with other literatures from other reporters. So when we come to the bulk, our main target, as you can see from D, our system come to metallic, no gap. We can say no gap. I mean, it is like metallic nature. Our calculated band gap is 0.6 electrovolts. This is really a wonderful result we got. So when I come to the lithium-ion transport in the bulk structure, you can see different channels, I mean, different pathways. As you can see from A, we have A, B, C pathways, lithium-ion pathways, and also we have A, E, F pathways along Z axis, and we have A, G, H axis, I mean, paths, lithium-ion diffusion paths along the Y axis into the crystal system. So from the calculated energy barrier, as you can see from B, along the channel AGH, the calculated energy barrier is higher. So it is very difficult for lithium-ion to diffuse along these channels. So when we come to the other passes, it looks fine, but still we need the energy barrier to be less than or equal to 0.5 electrovolt. Unless otherwise, it is very difficult for the lithium-ion successfully diffuse in these materials. So when you come to the bulk, when we come to the surface, 001 surfaces, you can see all the paths along ABC channels and EAB channel and ABD channel. All the paths are fine, as you can see from the figure. Look, all the calculated energy barrier are less than 0.4. So our system now becomes ionic and electronic conductor. This is a very wonderful work we have got, the results we have got in this calculation. So when I come to conclusion, surface free energies, when we see surface free energies in order of stability, 210 is greater than 010, and which is also greater than 001, and also 100 in order of their stability. But as I already mentioned, 001 has higher surface area coverage, so we choose that one. Unlike the bulk insulator, electronic analysis results reveal that there are superior 001 surface conductivity pathways in this material. So the NEP calculation confirmed unlimited and fast 3D lithium-ion diffusion on lithium manganese silicate 001 surface, unlike to the corresponding bulk phase due to large energy barrier. Thank you for your attention.
Okay, Thank you very much, Gamachis. Thank you. So you can share your screen, and now we should take questions. So if you have questions for Steve, questions for Mark, questions for Mireille, and questions for Gamachis, then you can ask now. You can ask in the chat, or you can ask them just by talking to us.
I have a question for Dr. Malonda, and it's related to the difference between bismuth and manganese. And I guess I would have expected bismuth to have stronger spin orbit coupling than the manganese, and I'm wondering how that plays out when we don't include non-collinear effects and that sort of thing. Is it more of a concern as you go to the heavier atoms, or does bismuth just not take part in the magnetic behavior?
Yeah. So Brice, the question is for you, Professor Brice. You can unmute yourself, Professor Brice, and answer. So it's about the manganese. Hello, Brice. Brice, you can unmute yourself and then talk. I don't know. He's not responding. Hello, Brice.
I should have asked it during his talk.
Yeah, but yeah. Hello, Brice. Okay. Okay. Let's take another question for someone else. So I assume Steve is still here, Mark is still here, and Gamachis is still here, and Mireille is still here also.
Steve in the chat.
Okay, a question for Steve. Yeah.
It's how did you account for basis set superposition error, and did you use localized orbitals, which is usually the case for molecular systems where there's basis set superposition area? And the question was from Michel Cote.
Thanks for the question. I guess this has to do with the electronic structure calculation. I have to say we had very little to do about the electronic part of the problem. So those questions about the basis set superposition error probably have to be viewed in a different way. But what I can say about the surface, from what the people who made it told us, is that it's made with the same type of approach that was used for instance, the MB pole potential energy surface of Paesani, Francesco Paesani. So it's more or less the same of the same order of quantum chemistry calculation, and it's not, I mean, they are reliable, if I can tell it that way.
Okay. Yeah, thanks.
Sorry, but Steve, in MCTDH also, doesn't the issue of basis set superposition come in?
Oh,
basis set superposition error come in, right?
Yeah, in MCTDH.
Fully forces, yeah.
No, in MCTDH, it's a variational method. So the basis, we know that when we increase the basis, we just go towards convergence, toward the exact result. So there is no force of that kind, I would like to say. No errors coming from that part. As long as your calculation have converged, it's fine.
Okay, I think you're right, because then it's not like you delete one molecule and consider another one. Okay, yeah. No. So this makes sense, yeah.
Yeah, I think it would be the case that when you have basis at superposition area error, the Hellman-Feynman-Palais force is the correct derivative of the imperfect energy.
Yeah. Okay. Yeah, Steve, I had a question for you. Oh, sorry, the other questions. George Amolo is asking Gamachis in the chat, your calculations assume defect-free structures. Can you tell from your work or literature how the presence of defects will affect the properties you have reported to us now? So Gamachis, the question is for you in the chat.
Okay. We didn't consider about the defect because, but in principle we can do that. But in our case, we did. We cleave the structure in different orientation, and then we compare the free energy for each surfaces. Then we found all the surface sound is fine. So, but for our purpose, we choose 001. For some, for others, I mean, or other group may can do that. Defect may have some impact for the electrochemical activity of the material. Thank you. Okay, another question, another point I should raise is also, okay, I am not sure, we didn't check the pH of the material because this is not for photocatalysis application. We need the material for cathode in lithium-ion battery. So maybe someone, I'm not sure actually, I didn't consider that one.
Okay.
And another question I should also answer here is from Mikkel. Yeah, when we do the NEP calculation, because I did the NEP calculation on surface, right, 001. So some lithium ion will be removed definitely. Yeah.
Okay. Thank you,
Yeah,
Gamachis.
follow up on this. Are you charging the system to account for the removal of the lithium atoms, or?
No, no. I didn't charge because just I do the surface right using some softwares, or technically you can do that manually, right? Different mechanism you can implement to find the interested surface. So after that you can do your NEP calculation, diffusion. So I didn't charge the system at all.
Okay. Thank you.
Yeah, thank you,
Gamachis.
Mikkel. Yep, thank you. But I have a question for Mark.
Oh yeah, okay. Question for Mark.
Yep.
From Gamachis. Mark, please.
Yes.
So Gamachis, ask your question.
Okay, okay. Yeah. Hello, Mark.
Hi.
Hi. So thank you for your nice presentation. Really, you are considering the most likely the same system with my calculation. So, but all the manganese, your system is rotated like with 12 oxygen or something like that, or what?
There's let's see, there's 12 oxygens, but then the ligands, there's these formate ligands, there's 16 of those.
Yeah, I have a question on top of that. So if manganese is rotated by 12 oxygen, how could we expect the Jahn-Teller distortion in that case?
Okay, so there's 4 water molecules in the system, and if you kind of think of the molecule as a plate, then there's 2 water molecules above the plate, and then 2 water molecules below the plate. And of course, they move very easily. And so each manganese has 6 neighbors, 6 neighboring oxygens, but the water molecules hover much further away from the manganese, and that is the Unteller distortion you're describing, and it splits the two-fold EG states at the Fermi level.
Yep. In my case, you know, it is tetrahedral. The manganese is rotated by 4 oxygen, right? To keep the symmetry, so there is some kind of like due to electron interaction or due to the ligand with the cation. I mean, oxygen with manganese. There is some kind of stretch or comprehensive in the system, right?
So
to keep the symmetry, the system to keep the symmetry, the John Taylor may happen, right?
I would think so. But what is the charge state of your manganese then?
It is 3 and 4.
3 and 4.
Sometimes,
okay, that's the same in this system, 3 and 4. And so is there do the sides of your tetrahedrons, are they equilateral or significantly isosceles rather than
stretch and compress, stretch or compress, Thank you.
That's very interesting. So,
thank you.
Okay. Any questions? Any other questions? I have a quick question for Steve. I asked in the chat, Steve, could you just use path integral molecular dynamics or centroid dynamics to calculate the spectra, the RR spectra? Has anybody done this? You could use it at low temperatures, so you have a lot of beads, but you'll be able to calculate the centroid, the spectra from centroid MD or from centroid MD. Has anybody done this for water dimer?
I think I've seen some works on this specific problem, but the issue is that you'll be able to see a spectrum. It can be correct, but you will not know the origin of the bands on in the spectrum. You will need a different type of analysis to know where they come from. And what we're interested in is to know what type of motion each of them represent. So that's why we go for that one rather than this other type of simulation.
Okay. Other questions? Okay, if no other questions, so let's thank all the speakers. So if you're in person, we'll clap and thank all the speakers. So we thank all the speakers, and I think at this point we can have a breakout room for 15 minutes. And there will be 5 breakout rooms that you can go into. Okay. So those 5 breakout rooms, you go in there and you can talk more with the speakers and ask them questions. After that, so you can do that for like 15 minutes. After that, we take a break and we now go for the poster presentations. So I think they will open the breakout rooms now. And then you can go talk with the speakers for 15 minutes. After 15 minutes, you'll be back here, and then we'll take a 5 minutes break or so, and then start the presentations. So I don't see the breakout rooms yet. Does anybody see the? Okay, I see now. Yeah. So if you click on the breakout room, there'll be many rooms you can go to. You should go to the room of one of the speakers that spoke today. Okay. Go to their room for like 15 minutes, discuss with them any other questions you have. Then we'll come back to the main room and we'll have a discussion. And then after that, we'll take a short break and then go for the full-fledged presentation. Okay, thank you. So you can just look for the names of the speaker and you go there. When you go to the room of the name of the speaker, so there's Mark Pedersen, you can go to his room. There's Stephen Ndéngue, you can go to his room. There's Brice, you can go to his room. And there's Gamachis, you can go to his room also. And Mireille should have a room also. Okay, there should be a room for Mireille also. Yeah, there's a room for Mireille, so you can go there and ask her the questions we are not able to ask her, and the questions we are shy to ask in presence of everybody. If you need help going into the rooms, let us know in the chat.
Richard, can you hear me?
If you need help going into one of the rooms, let us know now so that we can place you in the rooms you want to go. Richard is muted. Richard, you are muted.
Okay, now.
Okay, now we can hear you.
Yeah, yes.
So I don't have enough new videos to play today. So I was just going to use the break time to announce that I can go and I was going to go into one of the speaker rooms. Oh, wait, Tuna doesn't. Let me post some instructions for Tuna. So. I'm going to share my screen with instructions on how to join. So Tuna, you don't see the breakout room button at the bottom of your Zoom?
No,
okay. Can you tell me what you do see at the bottom of your Zoom?
I see participant, chat, share screen, record, live transcript, reactions.
Okay. Do you see more to the right if you keep going to the right?
No, I don't. I see the leave. And then on the left, I see mute and start video. I don't see.
Okay, let's try. Maybe if we put you in a room, then you can, then you will see them again. What is there a particular room you want to go to?
I want to go to the room where our poster is.
Okay. But we're not doing the posters yet, actually. But if you just want to go there, I can put you there. But the posters will happen after the break that's coming up.
Yes. And then in the meantime, also
put
you
me
can.
in the poster room because I don't see anything anyway. It will be hard for me to go from one room to another.
No, we'll put you in.
How about I put you in with Mark right now?
Okay.
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 But the other thing also, you can download a newer version of of Zoom and use the client. Okay.
Okay, but I'll put you in the Mark Pedersen room.
Okay.
Yeah.
Fine.
Thanks.
Thank you.
Okay. Let's see. I don't know why I assigned her to the Mark room. It looks like it's taking a long time.
Yeah, it depends on the
There it
connection.
goes. Yeah,
she's there now.
Yeah, wow, that was very slow. Okay, so I don't have enough new videos to play, so I thought I would just offer to people, I can go into a breakout room and just record them, giving their introduction to me, and then I can play those tomorrow. I usually edit the beginning and the end off a little bit, and then I boost the sound and add the name and the institution under the video. So I can do that this afternoon, but I thought it might be a simple thing to offer to people if they haven't done it yet, but they would like to.
That's a great idea. I just didn't think at all. And also we want to thank the helpers sometime. I never replied to you on that. Do you think it should be today or should we wait till tomorrow?
Well, it doesn't really matter. We have time today since I'm not going to show the videos. So how about I put up this slide? I prepared a slide. Let me share it and see what you think of it. Okay. Oh, well, I'll have to post it. Yeah, I overwrote it with something else. Okay, but if that sounds good, after the break, then I will just announce that. I put it on the web schedule that we won't have a poster video, we won't have introduction videos today, but I did get new ones. So I did get some new ones, and I'd like to have a few more. So then that way I can show them a few tomorrow.
Well, they were really good. So I hope
we get more. We don't have too many more. So that's why I thought, oh, I should offer today for people who just would like to give it a try. Right. Yeah. Okay. And I talked, email. I just emailed with, I think you saw it in my chat message.
With
Vimhindi.
Who is that?
Vimhindi. He couldn't come today, so he has connectivity problems today.
Oh, yes.
So I asked if he could pre-record a talk and send it to me. So then I thought tomorrow we could play the short talk if he cannot attend in person again.
Ooh, we might have difficulty because we're supposed to, do the closing remarks, and we have a full schedule.
Okay, I think it might work. I haven't heard confirmation from all of tomorrow's speakers yet. So yeah, so if we have a gap, then that will be okay. I just asked him to go ahead and pre-record something if he's able to do that.
Okay.
Yeah.
Well, that could be in a room if we need to.
Yes. So that's at least we'll have something. Otherwise, if he doesn't record and he can't join, then there's nothing at all representing him. Yeah. And let's see. So those are the main things. I'll finish this slide. And Omo, I have on my timer, we have about 5 more minutes left for this breakout room discussions. Does that agree with yours? Okay. I'm going to
actually, it's like 2 minutes more than mine, but it's fine. Yeah.
Okay. Yeah.
It's fine. Yeah.
Okay. Richard, I'm going to make a slide and put it up to identify the tech helpers. Okay.
Okay. Okay.
Now. Yeah. Just so you have their names right there in front of you.
Okay.
Okay.
Richard,
and we'll thank them.
Yes, that would be great.
So Richard, Sinead, and Amy and Renata, when do we discuss with everybody about I don't know, when do you have a closing discussion with everybody?
I think tomorrow, Omu, before the new videos.
Okay.
Is that all right?
So yeah. Oh, so before the videos, okay?
I think so. Or would you like it after the videos? It doesn't matter.
Oh, well, I don't know, but probably before, since the videos go with posters.
I think so.
So we can have it before. Yeah.
Okay. I think before is better.
Or before the break, either one. Which?
Yeah, I think before as well. We still have everyone and before they start breaking it into rooms.
As soon as we open the rooms, everybody runs into a room, even if there's nothing going on.
Exactly.
I wonder if they're just testing their connections. Yeah.
So let's see if I agree. Before what?
Before the videos.
Okay, before the videos. Very good. Okay. Okay, thank you. That's looking good.
So Amy, I sent you a comment in the chat.
Oh, sorry. That's a. Thank you.
Oh, Amy, we need to bring everybody back. Sorry, I forgot.
Okay. Okay, how's that, Omo?
Yeah, perfect.
Okay, I thought it's weird to put me in there, but okay, fine.
Yeah,
it's
yeah,
true.
yeah, yeah.
It's
I
true. So
wanted,
it's
yeah, okay. So you close the breakout room, right?
okay.
Okay, yeah, let's see. Yeah.
I'm just closing them. I didn't send any message.
Yeah, it's fine.
Okay.
Zoom sends a message to them. Yeah. So Richard is going to say something now, right?
Yes.
Okay.
Richard? So
Yes.
the breakout rooms will be closed in about 10 more seconds. Then we know that everybody is back in the main session.
Okay.
So not
Good.
quite yet, just 10 more seconds. Yes.
So would you and Steve, give thanks to the volunteers?
No, Richard, you give thanks to the volunteers.
Okay, but then let me see if I can. Okay, can you help me then?
Okay.
Okay, I'll give thanks, but you say something more about, anything about them, what they do, what they're from, and where they're from, or anything like that. Okay.
Okay.
Okay, is everyone back in the main room?
I think so. Yeah.
Okay, so I would like to especially thank the tech volunteers. This is a difficult job, and it's really needed to have help and to make this Zoom meeting work. And I've been going around to different rooms, and I see each of you appearing in the rooms, and I'm sure that means that you're helping and making things work during this meeting. So I'm not going to be able to pronounce all the names, but Veronique, Matthew, Olivier, is that how we say it? Rosmael, Sunday, and Hervé. It is just wonderful that you're helping. And maybe Steve and Amy could say where each of you is from.
I'll go first then.
Yeah.
Veronique and Olivier are in Michel Cote's group. And I joked with Michel that it proves the stereotype I have in my mind that Canadians are very nice and friendly people. That's what I think.
This is actually true. This is actually true. I've visited Canada twice, and the people are very friendly and warm.
And Matthew
right.
is a professor at Southern Connecticut State University, and it also confirms my stereotype that Connecticut faculty are very nice people.
Good.
So I'm going to continue. Rosmael, Sunday, and Hervé are all PhD students at the East African Institute of Fundamental Research. So they took time off from their research work to help for this meeting, but not only that, they were there for all the preparation meetings that we have for this event. So it's very kind of them. They are all in the condensed matter session. Hervé is a PhD student with me. Sunday is a PhD student with Omolulu. Rosmael is a PhD student also with Omolulu. So we thank them all for what they've been doing, and they're being very helpful for us.
Oh, good. And are they from different countries?
Yes, Hervé is from Cameroon, Sunday from Nigeria, and Rosmael also from Cameroon.
Really nice. So thanks to everybody that's doing the participation and helping the rest of the people in this Zoom conference. Thank you.
Yeah. Thank you very much for all the time and effort you put into it. You know, I get these emails from Steve saying there's a meeting at so time and I don't attend. But the other people there all attend. Because there were a lot of meetings that they had. So thank you very much, Veronique.
Okay, let's everybody thank them as waving or clapping or any way you can.
Oh, we clap.
Yeah.
Oh, we can clap. Okay.
Okay, thank you.
Okay.
Okay,
so I'm going to stop screen sharing now. And actually, I don't have a camera here. Sorry, on this camera, but on this computer at any rate. So now we're going to open the rooms again for breakout rooms. And I wanted to say that I received a few more short video introductions from people, but we'd like to have more because we know that not everybody submitted one. So if you didn't submit one and you would like to, but you kind of don't know how to do it and you want to talk to a human, I'm going to go to the poster to the speaker ready room. You'll see me there on the USAfrI Amy, and then you'll just talk to me and I'm going to record that. And then this afternoon and this evening, I will edit them all. Whoever shows up, you're welcome to show up anytime. I'll be here. And then I'll edit them all together and we'll show them on Friday. So I know that I received 2 more today and I'm definitely going to play those. But if we get more this afternoon, then I'm going to include those. So we can record it now, or you can email me something. If you email me this afternoon, that would be great because it takes me a little time to put them together. Okay, so we're going to open all the rooms again and for the poster sessions. And if you want to take a break from the poster sessions, you can of course see me and I will record you introducing yourself and play that tomorrow. Anything else, Richard or Omalolu?
Yeah, so if you're giving a poster, there's a room with your name on it. So just look for the room and join and wait. People will come to talk to you about your poster and discuss with you. And others, others who are not giving posters, we just visit the rooms that so people are in and discuss with them. Thank you very much.
Okay.
And when Amy said this afternoon, she meant afternoon in the central part of the United States. Right?
Right. So kind of in the next 6 hours would be great.
Okay. Okay.
Okay. All right. I'm going to open the rooms now.
Thank
the break
you.
rooms. Thank you.
If you would like to join a room, but for some reason you cannot join, maybe you cannot leave the room you're in, let us know. And Amy or one of the volunteers, tech volunteers, will put you in a particular room. So this usually happens if you don't have the latest version of Zoom, the Zoom client or the Zoom app. So what happens is you may not be able to go to a room without being assigned.
So we should
You
have
can
Zoom
just,
installed on our computer to be able to see the rooms because I don't see any room.
oh, if you don't see a room, that means you don't have, it's possible that you don't have the latest Zoom version. So if you install the latest Zoom client, then this will help.
Okay.
You should see some squares that say breakout rooms. Do you see that?
I do not.
Okay, so the share screen record live transcript breakout rooms. Okay, if you don't, then you could try to install the latest version of Zoom, or if you want, you can ask and someone could put you in a room. Which room would you like to go?
I have to be in a poster presentation, but I don't know what room is that.
If you, oh, I see. Yes, you have to be in a poster presentation. So Amy, is Amy still there?
No,
No, she's not.
Okay, so one of the volunteers is a host or co-host, so they can put you in the room.
Brice, are
Henry,
you there? I'm sorry, go ahead.
oh, I was saying, is Henry there? Or Rosemel? Rosemel, could you make me host or co-host?
Yeah.
Oh, Olivier is the host now. So Olivier, could you make me co-host, please? We'll move you to the room you want to go just now. Hello, Olivier. Oh, I think Amy went to a particular room. Zara, please give me a few minutes. We'll get to you.
Hello, Brice, are you there?
Sorry, Amy, hello? Hello, Amy, are you there? Okay. Hello, Sunday. Sunday, please, could you put Zara in the room for her presentation? So again, if you would like to join a room and you cannot join a room, let us know, and then we'll try to assign you to the room of your choice.
Hello, Molulu.
Hello.
Hello.
I'm Esfin.
Hello, nice to you, Doctor. Oh, I was in the breakout room for a poster presentation. You didn't visit my poster.
Oh, but you should still be there, no?
Ah, I thought it is finished.
No. Oh, yeah, technically we should finish at 6,
Okay.
which will be 7 in Ethiopia.
Yes.
But we don't shut the place. We allow people to stay there and hang out. And then different people can come there.
Okay.
Did anybody come to your poster?
Yes. Yeah, a lot of people came there.
Including me.
4 or 5, yeah.
Oh, okay. Can you let me? Yeah, you go there, I go there, and then I'll see your poster.
Okay.
Do you?
Okay, yes, I like to see you there. Okay.
Okay, thanks. I'm still looking for your name.
Yes, Mesfin Asfaw.
Yeah, I see.
Where is it? Oh. Okay.
Sunday, are you there? It's Amy.
Hello, Ami.
Hi, Sunday. How are you doing? You're feeling better today? Are you feeling better today? Hmm. I'm hearing some static. I'm hearing some static. I was going to ask you and Rosmael if Sunday you felt you could take care of the recording, stopping, starting, and pausing tomorrow in case Rosmael needs a break. Somehow it sounds very staticky. Maybe your microphone is. Yeah. Okay. Yeah, that sounds good then. Okay, Sunday. So then that will be your activity. Rosmael, you can take a break from that. And then Veronique is going to spotlight the people as they talk. And then I'll set up the break rooms. Unless, Rosmael, you would like to set up the break rooms. I don't know if Rosmael is still here. So I'll ask Rosmael if she wants to set up the break rooms, practice doing that. And then if not, I can do it. So no biggie. And
Okay, I want to do that.
You'll do that with me? Okay. Yes. So today we got feedback that people really want to see the name of the person and the name of their poster. So I usually do that. I have the Google Sheets open and then I just copy, paste. So the whole name of the poster won't usually fit, but you know, like the first 3 or 4 words will fit. So I would propose that that happens tomorrow after the talks get started, you know. So like once the 4 short talks start, then you can start making the breakout rooms. Okay? Okay, great. And then I'll be here, so if there's any issues, you can just let me know. But that was a specific request we got today to include the name and the breakout room. So the person who requested that isn't here, so I can say that. Okay, well, that's all I have for you today, unless you think there's anything else. I think that's all. So I'll wish you a good night. I know it's nighttime for you.
Okay, thank you.
Thank you. Thanks, Rosmael. We'll see you
Thank
tomorrow.
you, Annie.
Okay, thank you, Steve.
See
And
you.
we'll see you Sunday tomorrow.
Are you closing the rooms or?
I
because
didn't
there's-
close them. Are there still people in them?
Yeah.
Oh, and Miss Finn still has some people. Oh, Mark still
Yeah.
has people. Okay, maybe I ought to go into Mark's room and record a little bit.
Yeah.
I left
it's not-
my room.
It's not actually Mark who's. Oh no, he left his rooms.
No, oh, it's his poster students. Yes. Yeah, it's
Okay.
the students. Yeah. Okay, I'm going to go there.
Okay.
Okay.
just left me by myself. Yeah, of course. Because there's a million cycles always from which one? No. Why are you doing this? I mean, why? For a long time, your sister recently came into possession of gold. Plenty of cities, right? Gold. Beautiful ones. But you see, I have an exile. French. Now, I sure. I am not weak. And when I want the friends. I know sometimes you need persuasion, right? And so I help you. He's nice man. And paralysis of muscles. Once, I not be able to read. This happened maybe 3 hours. No, I am cured of this buildings. I'm cured for mine. I see that. Smoke. Wait, look at his face. Who's that? I care about yeah, that sounds about right. Got it. Catch over the top. Yeah, it's iron and action to prevent the nervous system from carrying vascular muscles, flexing, and spine, nervous stimulation. I do what you just said, but that doesn't sound good. Very true. Yeah, we should have some down start journal. That's great. So all we have to do is get it to the poison takes over this entire body. John, journal. Administer this to the patient and you know, I don't want to know this is seems like you have another chance to lie to me. I am out in the field with you and less than 1%. This is damn well my business. It was cold. So Matt was dead. I was low priority.
Okay, so I'm going to stop the